Northern European ancestry. Northern European ancestry tells the story of adaptation to scarcity, of light, warmth, and time. Across Scandinavia, the Baltics, and the British Isles, evolution favored pale, low melanin skin that could draw power from even faint winter sunlight. This trait turned fragile light into life, producing vitamin D to strengthen bones and immunity where the sun barely rose. At the same time, herding cultures shaped a second advantage, lactase persistence. The ability to digest milk into adulthood became common, offering hydration, calories, and calcium, long before refrigeration or green fields. Milk was the original superfood smoothie, minus the blender, and was key for Northern European ancestors to survive. Generations living on butter, fish, and meat developed efficient fat metabolism and brown fat thermogenesis, mechanisms that conserve heat and burn calories for warmth. Blonde hair and blue eyes, while visually distinct, are simply echoes of this light-adapted chemistry. But modern life twists the design. Fair skin burns easily under strong sun, and long winters indoors still cause vitamin D dips, despite those ancient advantages. Evolution built a solar panel, but now it lives under fluorescent lighting. Northern ancestry is a lesson in refinement. To endure is not to resist the dark, but to learn how to live within it. South Asian ancestry. South Asian ancestry reflects thousands of years of adaptation to intense climates and diverse diets. In regions stretching from Punjab to Bengal, bodies evolved to handle both scorching plains and monsoon humidity. The typical build, lean with slender limbs, helps release body heat efficiently, reducing the risk of overheating in tropical environments. Basically, the original built-in cooling system before air conditioning or fans were invented. Genetically, many South Asians carry high numbers of AMY1 gene copies, which boost the body's ability to digest starch from grains like rice and wheat. This trait supported survival in agricultural societies that depended on carbohydrates from many different crops. Their bodies look at a plate of biryani and say, "Challenge accepted." Some groups also developed partial lactose tolerance, reflecting a history of herding and dairy use in certain castes and regions. These advantages created remarkable dietary flexibility and heat resilience. But in today's calorie-rich settings, the same energy-conserving physiology can become a liability, increasing the risk of diabetes and heart disease even at lower body weights. Evolution shaped efficiency, but efficiency in a world of excess can have its costs. East Asian ancestry. East Asian ancestry has a remarkable package of surface-level and metabolic traits, fine-tuned for life in humid, variable climates from China, Japan, and Korea. One genetic variant stands out, the EDARV370A variant. Found in over 90% of East Asians, it produces thick, straight hair and a higher density of sweat glands, a combination that shields against sun and rain while keeping the body cool. It's basically waterproof and self-cooling long before Gore-Tex came onto the scene. Other genetic adaptations further shape how fats and sugars are processed. These reflect a history built on rice, vegetables, and low-meat diets. Energy efficient and stable. Thicker hair, shovel-shaped incisors, and even subtle differences in melanin are all part of a climate-ready toolkit. But every design has flaws. Mutations like the ALDH2 STAR2 variant help discourage heavy drinking by triggering the infamous Asian flush. It's nature's way of saying, only one drink tonight. But this mutation also raises certain cancer risks. In modern environments, those same metabolic and pigment genes can clash with new conditions. High sugar diets, indoor living, and limited sunlight. What once maintained balance in rice fields and open air now struggles to adapt to cities and screens. Evolution gave harmony, but modern life keeps testing its rhythm. Southeast Asian ancestry. Southeast Asian ancestry carries a precise adaptation to one of Earth's most demanding habitats, the hot, humid forests of the tropics. Populations from Vietnam, Thailand, Indonesia, the Philippines, and Malaysia evolved compact, lean physiques that shed heat quickly. Shorter stature and slender builds increase surface area relative to body mass, a natural design for staying cool when the air feels like hot soup. Think small frame, big ventilation. Genetically, these groups excel at sweating and at holding on to crucial salts and electrolytes, even in extreme humidity. Many share the AMY1 starch processing advantage, fine-tuned by centuries of rice and root crops, and metabolic systems suited to low-fat, high-carb diets. Dark to deep brown skin tones reflect a powerful sun defense strategy, enough melanin to block UV without trapping excess heat. But these same traits come with trade-offs: limited vitamin D synthesis, sensitivity to cold, and faster weight gain on westernized diets. The body that once crushed tropical farming now panics with fast food. Evolution favored survival in the jungle, a reminder that efficiency depends entirely on the environment. Sub-Saharan African ancestry. Sub-Saharan African ancestry embodies two evolutionary triumphs, strength and immunity. Across millennia of exposure to tropical heat, parasites, and relentless sunlight, these populations developed bloodlines tuned for endurance and defense. Genetic adaptations like the sickle cell trait and G6PD deficiency reduced the impact of malaria, transforming what was once a deadly threat into a manageable trade-off. Their immune systems looked at malaria and said, "Not today." Another defining legacy lies in muscle biology. Many sub-Saharan lineages carry the ancestral ACTN3R allele, which fuels fast-twitch muscle fibers, the same type that powers explosive motion. From West African sprinters to East African endurance runners, these traits continue to shape global athletic performance. Combined with lean builds, efficient sweating, and dark melanin-rich skin that protects vital nutrients, this ancestry reflects precision engineering for life in extreme environments. But every advantage balances with cost. Two sickle cell gene mutations cause disease instead of protection, and the same immune systems that fought parasites for millennia may overreact in new urban settings, increasing inflammation risks. Still, the resilience of sub-Saharan ancestry is unmatched, a heritage of strength written into blood and muscle. Middle Eastern and North African ancestry. Middle Eastern and North African ancestry tells a story of persistence in one of Earth's harshest environments, the desert. Populations from Arabia to Morocco evolved systems that conserve water, resist heat, and draw nourishment where little exists. The kidneys of desert dwellers became masters of precision, conserving every drop, while sweat responses balanced cooling with minimal fluid loss. Perhaps the most famous trait is lactase persistence, the ability to digest milk into adulthood. For herders of goats and camels, milk wasn't just food, it was hydration disguised as nutrition. Milk really was the MVP back in the day. This adaptation still defines the region, from Bedouin encampments to modern kitchens where dairy remains central. Genetic variants promoting salt retention, moderate to dark melanin, and lean builds further supported survival under relentless sun and scarce water. But modern life has flipped the equation. What once saved lives in drought now fuels hypertension and kidney strain under salty, calorie-rich diets. Still, these bodies remain built for resilience, heat-tolerant, energy-efficient, and unshaken by extremes. Their biology is desert-tested, capable of thriving when the world burns and conserving when the environment forgets to give. While some ancestors learned to survive 118 degrees Fahrenheit summers, modern descendants complain about room temperature. Central Asian ancestry. Central Asian ancestry traces back to the nomads of the steppe, the Mongols, Kazakhs, Kyrgyz, and others who lived where grass meets sky. Their environment demanded stamina, endurance, and resilience. Generations on horseback shaped broad chests, strong legs, and powerful lungs capable of thriving across endless plains. Cold winters, thin air, and constant motion carved bodies made for survival, not comfort. People from this region were the original CrossFitters, except their gym was just the vast landscape. Genetically, these populations show adaptations for both high altitude and high protein. Many carry unique genetic mutations that enhance oxygen use and support heavy meat and dairy diets. Kumis, butter, and mutton were daily fuel, not indulgence. Centuries of contact with livestock and travelers forged a rugged immune system that could handle nearly anything. But modern life brings its challenges. Immune systems once trained by horses and hardship now face processed food and office chairs. It's hard to conquer empires when the enemy is your cholesterol. The steppe body remains a symbol of endurance, proof that strength evolves where the horizon never ends. East African Highlander ancestry. In the East African highlands, human physiology achieved something extraordinary. Populations like the Amhara, Oromo, and Kalenjin thrive above 2,000 meters, where oxygen is scarce, and most people would gasp just climbing stairs. Yet their blood remains calm. Hemoglobin levels stay near sea level norms, while oxygen uptake remains astonishingly high. Instead of making thicker blood, they became better at using what little air there is. Researchers still can't pinpoint the secret. Possibly greater capillary density, faster oxygen diffusion, or muscle mitochondria working in overdrive. In short, they have an off-the-shelf engine, but they perform at much higher levels. These traits fuel unmatched endurance. Kenyan and Ethiopian runners glide through marathons with lungs built by altitude and legs tuned for economy. Their genes don't just endure thin air, they mastered it. Yet even this design has limits. Constant low oxygen can strain pregnancy and kidney function, and their lower blood viscosity can make sudden oxygen drops harder to handle. In the thin air of the highlands, the body learns a quiet lesson. Endurance is not just muscle strength. it is efficiently using what little resource the environment gives you. Indigenous American ancestry. Indigenous American ancestry reflects one of humanity's greatest physical legacies, perseverance. Descended from ancient migrants who crossed from Siberia to the Americas, these populations adapted to every landscape imaginable: tundra, desert, jungle, and mountain. The result is a physiology built for motion and oxygen efficiency. Among the Tarahumara of northern Mexico, runners sustain oxygen uptake nearly 10% higher than neighboring groups, moving barefoot for hundreds of miles through canyons. Their bodies use oxygen like an artist uses color, sparingly, precisely, beautifully. Modern marathoners wear carbon plates. These runners wear determination and dust. Genetic studies show lean frames, powerful aerobic systems, and high blood oxygen retention even at altitude. In the Andes, Quechua and Aymara Highlanders evolved further, maintaining strong hemoglobin levels in large lungs that turn thin air into usable power. But adaptation has a price. Metabolisms, once tuned for scarcity, now meet abundance, fueling obesity and diabetes in a sedentary lifestyle. Highlanders risk excess hemoglobin thickening the blood, while others face cold sensitivity or infection risk due to low fat reserves. Still, the legacy persists. To move long and breathe deep, that was survival's command. The ancestors ran continents. Their descendants still run history's longest race. Pacific Islander and Polynesian ancestry. Pacific Islander ancestry carries the legacy of endurance, strength, and survival at sea. Across Samoa, Tonga, Hawaii, and Aotearoa, centuries of voyaging and island living forged a physiology that stores and spends energy with remarkable precision. Genetic research highlights the CREBRF variant found in roughly 40% of Samoans, a thrifty gene that helps store fat and muscle efficiently during times of abundance. For ancient navigators crossing vast oceans, it meant security through famine and storm. It's basically evolution's version of packing extra snacks for a long road trip. These same genes shape the distinctive Pacific build: broad frames, dense muscle, and powerful strength for a given body size. Traditional diets of fish, taro, coconut, and root crops further tuned metabolism to handle fats and carbohydrates with ease. In combination, these traits created bodies capable of paddling canoes across oceans, farming volcanic soil, and enduring isolation with calm precision. Modern gym goers call it functional fitness. Islanders just called it Tuesday. Today, those same efficiencies face modern pressures. In an environment of constant abundance, the thrifty metabolism once meant for scarcity now drives soaring rates of obesity, diabetes, and heart disease. Yet the physical legacy remains extraordinary, a lineage built for movement, endurance, and survival across the world's largest wilderness, the Pacific Ocean. Arctic and Inuit ancestry. Arctic ancestry represents one of humanity's most remarkable engineering feats, turning fat and frost into fuel for life. The Inuit and related peoples of Greenland, Alaska, and Siberia evolved specialized metabolisms that thrive where almost nothing grows. Their FADS1 and FADS2 gene variants rewire fat processing, converting omega-3 rich marine oils directly into energy and body heat. In other words, they burn blubber like a clean fuel source instead of storing it. Meanwhile, most modern diets see fish oil and call it a supplement. Additional genes, such as TBX15, enhance brown adipose tissue, the heat-generating fat that warms the body from within. Shorter limbs, compact builds, and efficient oxygen use reduce heat loss and conserve energy. These traits together create a physiology capable of enduring minus 22 degrees Fahrenheit winters, a system that quite literally burns calories to survive. Specialization comes at a cost. When traditional diets shift to Western foods, the same fat-processing genes struggle, leading to cardiovascular strain and nutrient imbalance. High mercury intake from marine food also poses risks, and vitamin D deficiency rises when old diets fade. Still, Arctic genetics tell a rare story. Survival not by resisting the cold, but by mastering how to turn it into fire. That's evolution's version of central heating. All natural, highly efficient, and without the electricity bill. Balkan ancestry. Balkan ancestry reflects a long history lived at a global intersection, where civilizations met, armies crossed, merchants traveled, and genes mingled. Across centuries, this region absorbed layer upon layer of immune-related diversity as Greek, Roman, Ottoman, and Near Eastern lineages intertwined. The result is a population with unusually rich genetic diversity in immune pathways like the HLA genes, granting a broad defensive repertoire against infectious disease. In essence, Balkan biology functions like a multi-key immune system. If one pathogen bypasses a particular genetic defense, Another variant often stands ready to intercept it. This diversity shapes present-day physiology. Broad antibody profiles, resilient responses to historic plagues, imbalanced susceptibility across many immune challenges all mirror this mosaic heritage. Even the region's mix of physical features, light and dark, northern and Mediterranean, echoes the melding that built such immune depth, while climates ranging from alpine cold to Adriatic heat further blended adaptive traits. But diversity carries complications. A wide gene pool means rare recessive variants occasionally pair unexpectedly, and complex immune networks can heighten inflammatory tendencies in a small subset of individuals. These risks become sharper when modern environments alter microbial exposure or lifestyle balance. Still, Balkan ancestry stands as a testament to the resilience born from mixture, an immune architecture strengthened by centuries of crossroads and convergence. Aboriginal Australian ancestry. Aboriginal Australian ancestry begins in one of the world's harshest climates, the Australian continent, where scorching days and cold desert nights shape the human body with relentless precision. This lineage is often defined by tall, slender frames, long limbs, and some of the deepest natural skin pigmentation outside Africa. Traits that form a living dialogue with heat, light, and dryness. These physiques function as natural thermal regulators. Long limbs disperse heat efficiently, while a lean build releases warmth during the day and conserves it at night. Many Aboriginal groups also carry a thyroid-related genetic variant that tempers the body's usual heat response signals, allowing internal temperature to rise safely before sweating begins. In a land where hydration once meant survival, this was an extraordinary advantage. History shaped perception as much as biology. Desert peoples adapted to scanning wide, dim landscapes, giving rise to culturally refined night awareness, more a product of practiced observation than genetic rewiring. Yet every adaptation carries its balance. High melanin shields from UV, but slows vitamin D production, and the muted fever response can mask infection. Still, this ancestry stands as a testament to quiet resilience, an evolutionary conversation between body and environment written across millennia. Tibetto-Burman ancestry. Southwest Chinese and Tibetto-Burman ancestry, represented by Tibetans, Sherpas, and Highlanders of Yunnan and Sichuan, carries one of the most striking human adaptations on Earth: mastery of life in thin air. On the Tibetan Plateau, where oxygen drops to nearly half of what is seen at sea level, these populations evolved a physiology that treats hypoxia not as a threat, but as a familiar state. Variants in genes like EPAS1 and EGLN1, inherited in part from ancient Denisovan-like humans, reshape the body's response to low oxygen. Instead of overproducing red blood cells until blood grows dangerously thick, Highlanders maintain normal hemoglobin while enhancing oxygen delivery through expanded chest cavities, higher resting breathing rates, and elevated nitric oxide that dilates blood vessels. The effect is quiet efficiency rather than strain. Functionally, these traits allow hard labor at altitudes that leave most feeling severe altitude sickness. Sherpas climb the Himalayan mountains with extraordinary ease. Tibetan farmers till fields above the clouds, and high-altitude pregnancies succeed where lowlanders struggle. But specialization has its costs. Lower hemoglobin at sea level can slightly blunt peak athletic power, and certain high-altitude gene variants may behave unpredictably in rich oxygen environments. These vulnerabilities sharpen when individuals transition to lowland lifestyles their biology never evolved for. Still, this ancestry stands as a pinnacle of rapid human evolution, bodies shaped by mountains, cold winds, and the thin, austere breath of the world's highest home. Mediterranean ancestry. Mediterranean ancestry emerges along coastlines where sunlight is abundant, seasons are gentle, and life grew around orchards, vineyards, and the sea. Here, generations carried forward an olive-toned complexion, moderate melanin that softens the sun's intensity while still inviting steady vitamin D synthesis. This balance is one of the region's signature advantages, a skin biology tuned for bright days without the fragility of easy burning. Within the body, subtler protections appear. A long heritage of consuming olives, fish, grapes, and herbs didn't simply shape culture. It shaped metabolism itself. Genes influencing lipid processing, including those tied to the papuan enzyme, respond strongly to monounsaturated fats, guarding blood vessels from oxidative damage. Combined with diets rich in antioxidants, this created a physiology that leans toward higher HDL, lower inflammation, and durable cardiovascular health. Evolution favored those who thrived in sun-drenched agriculture, bodies that store fat more safely beneath the skin, bones fortified by daily light, and metabolisms comfortable with energy-dense oils. Its trade-offs remain familiar. Moderate melanin can still permit sun damage, and lactose intolerance is historically common. Studies show lactose intolerance rates can go up to 75% in specific Greeks and 78% in Lebanese adults. Yet the deeper story is harmony, biology shaped by coastal light, fertile soil, and the quiet medicine of traditional foods. Khoisan ancestry. Khoisan ancestry represents one of humanity's oldest and most versatile genetic lineages, a reservoir of diversity that has endured in southern Africa for tens of thousands of years. Instead of evolving around a single dramatic mutation, the Khoisan retained an extraordinary breadth of genetic variation, giving their populations a wide biological toolkit for survival. This diversity acts as a natural buffer. When climates shift, foods change, or diseases emerge, some individuals almost always possess alleles suited to the new challenge. In ancient foraging societies, this meant metabolic flexibility, variable immune strengths, and adaptive physical traits that collectively promoted stability in the face of drought, feast and famine cycles, and environmental extremes. Functionally, Khoisan physiology reflects this broad adaptability. Efficient kidney concentration supports life in semi-desert landscapes. Distinctive fat storage patterns help buffer against seasonal scarcity, and rapid metabolic shifts allow effective use of both lean periods and abundance. Even their calm, measured stress responses mirror a biology refined by the demands of long hunts and unpredictable environments. But diversity, too, comes with challenges. Lack of historic exposure to outside pathogens left some Khoisan groups vulnerable to introduced diseases like smallpox, and highly individualized genomes can complicate standardized medical treatments, challenges that sharpen when traditional lifestyles give way to rapid modern change. But Khoisan ancestry stands as a living archive of humanity's earliest adaptability, proof that genetic breadth itself can be an enduring advantage. Amazonian ancestry. Amazonian ancestry reflects a physiology shaped by one of the most pathogen-dense environments on Earth. In the rainforests of Brazil, Peru, Colombia, Bolivia, and Venezuela, indigenous communities evolved immune systems finely tuned to confront parasites, fungi, insects, and vector-borne diseases that once overwhelmed outsiders. High frequencies of specialized HLA alleles enhance recognition of tropical parasites, while rare variants in genes such as PPP3CA strengthen T-cell activation and even reduce the ability of Chagas-causing parasites to invade the heart. At the same time, adaptations in innate immune receptors dampen excessive inflammation, allowing strong microbial defense without the damaging overreaction typical of chronic infection. The result is an immune system that balances vigilance with restraint, an elegant solution to constant microbial pressure. These advantages manifest in elevated baseline antibodies, efficient parasite clearance, and remarkable recovery from repeated infections, in large spleens, controlled inflammation, and metabolic strategies that protect growth during illness reflect the rainforest's evolutionary demands, but specialization can carry modern vulnerabilities. Hyperactive immune wiring can misfire in cleaner urban environments, increasing risks of allergies, asthma, or metabolic imbalance, and certain adaptations remain highly specific, offering little defense against novel pathogens. These challenges sharpen when Amazonian physiology leaves the ecological context that shaped it. Amazonian ancestry stands as a profound example of pathogen-forged resilience, bodies and immune systems trained by the relentless pulse of the rainforest. Slavic ancestry. Slavic ancestry carries a quiet toughness shaped by centuries of winter, woodland, and waves of epidemics. Across Russia, Poland, Ukraine, and the broader Slavic world, populations evolve subtle but powerful strengths in both cold tolerance and innate immunity. Variants in toll-like receptors, interferon pathways, and other first-line defenses prime their immune systems to react quickly, producing strong antiviral responses that often shorten the course of common infections. Meanwhile, life in vast cold plains and icy forests favored efficient thermoregulation, robust subcutaneous insulation, steady peripheral blood flow in freezing conditions, and a metabolic rhythm that maintains warmth with less discomfort than many other groups. These traits surface in everyday resilience, fast recoveries, tolerance for sudden temperature swings, and ease with winter rituals like icy plunges or steam and snow transitions. Even historical observers noted how Slavic villagers weathered epidemics or bitter winters with surprising stamina, yet these strengths carry modern challenges. Heightened inflammatory potential can raise risks of autoimmune disorders. Cold-adapted metabolisms can encourage weight gain in calorie-dense environments, and strong fever responses may strain the body during illness, effects that sharpen when ancient adaptations meet modern lifestyles. Still, Slavic ancestry reflects a physiology tempered by frost and fortitude, an inheritance built on endurance, grit, and the hard lessons of northern landscapes. Melanesian and Papuan ancestry. Melanesian and Papuan ancestry carries a rare inheritance, the highest proportion of Denisovan DNA found in any living population. In the tropical highlands and dense forests of New Guinea, this ancient legacy became a quiet advantage. Genetic variants passed down from Denisovan ancestors appear in immune pathways, shaping responses to parasites, viruses, and the microbial richness of equatorial terrain. These adaptations form a subtle but powerful defense system, refined through thousands of years of pathogen exposure. Physically, this ancestry is marked by some of the darkest natural pigmentation on Earth, rich eumelanin shields DNA from extreme UV radiation, guarding folate reserves and preventing deep tissue damage under intense tropical sun. Combined with efficient sweating and muscular, heat-adapted builds, these traits support survival in climates defined by humidity and relentless sunlight. Another notable feature is the presence of naturally blonde hair in some Melanesian populations, particularly in the Solomon Islands and Vanuatu. This is due to a specific gene mutation, distinct from the one causing blonde hair in Europeans. This is a textbook example of convergent evolution, when two unrelated populations evolve the same visible trait independently through different genetic mechanisms. Evolution rewarded resilience, immune systems tuned to unfamiliar pathogens, bodies built for heat, and metabolisms shaped for feast and famine cycles. But advantages carry their shadows. Very high melanin slows vitamin D synthesis, immune hyperreactivity can raise autoimmune risk, and thrifty genes become liabilities under modern diets, high in sugar and saturated fats. Still, this ancestry stands as a living archive, where ancient humans, tropical ecosystems, and deep time converge in the biology of a people. Basque ancestry. Basque ancestry reflects a rare form of continuity, an ancient gene pool maintained with remarkable stability in the Pyrenean Mountains. For thousands of years, Basque communities experienced limited outside mixing, allowing their lineage to develop a genetic baseline with fewer harmful mutations than many neighboring populations. This stability acted as a quiet safeguard. Recessive disorders that spread elsewhere in Europe never took hold here, and natural selection gradually reduced the impact of those that did appear. High frequencies of O blood type and Rh negative status stand as markers of this distinct heritage, echoing a lineage preserved across deep time. Functionally, this translates into a population historically marked by lower rates of congenital diseases, fewer metabolic disorders, and strong continuity of health across generations. Archaeological and medical records alike highlight communities with robust physical development, steady cognitive function, and fewer hereditary conditions that interrupt lifespan or vitality. Yet continuity brings its own vulnerabilities. Isolated gene pools can amplify the rare harmful variants that do exist, and limited immune diversity may leave some individuals more susceptible to unfamiliar pathogens, especially in modern globalized environments. These risks can become sharper when historic isolation meets contemporary mobility and lifestyle shifts. Still, Basque ancestry represents a living archive of Europe's deep past, an enduring lineage shaped by mountains, resilience, and the quiet strength of genetic stability. Southern African ancestry. Southern African Bantu-associated ancestry carries one of humanity's most formidable biological shields, layered genetic defenses against malaria. Across regions, once dense with Anopheles mosquitoes, survival favored individuals with blood traits that made it harder for the Plasmodium parasite to multiply. Sickle cell trait, perhaps the most famous, alters red blood cell shape under low oxygen, disrupting the parasite's life cycle. But this is only one line of defense. Many Bantu heritage populations also carry G6PD variants that create a chemically hostile environment inside red blood cells, hemoglobin C or thalassemia traits that limit parasite growth, and immune alleles like HLA-B53 that enhance early pathogen recognition. Each trait provides moderate protection. Together, they form a multi-layered biological fortress. Functionally, these adaptations reduce the risk of severe malaria, especially in childhood. Mild chronic anemia, slightly altered red cell structure, or unique enzyme patterns become protective quirks. Silent shields passed from generation to generation. Historical accounts consistently show local endurance against malaria, where unadapted outsiders suffered extreme mortality. But layered defenses bring layered complications. Double copies of these mutations can cause sickle cell disease, a painful and serious blood disorder. Serious blood disorders and G6PD deficiency heighten sensitivity to certain foods like fava beans and medications. Traits once beneficial can become liabilities when malaria is no longer the biggest problem. These issues intensify when ancient survival strategies encounter modern medical and dietary environments. Still, this ancestry reveals a profound evolutionary triumph. Human biology shaped by relentless selection, turning blood itself into a resilient, adaptive battleground. Caribbean ancestry. Caribbean ancestry is shaped not by a single environment, but by the meeting of worlds. Across these islands, African, European, Indigenous, and South Asian lineages blended into one of the most genetically diverse populations on Earth. This mixture created a rare advantage: metabolic flexibility. Many individuals inherit alleles that excel at carbohydrate processing from Asian ancestors, alongside genes for efficient fat metabolism or lactase persistence from European lines, and muscular efficiency and heat resilience from West African heritage. The result is a physiology capable of adapting to a wide variety of diets, climates, and physical demands. This diversity shows in daily life. Some carry high amylase levels suited for starchy tropical foods, while others digest dairy with ease. Medium to dark brown skin provides sun protection, yet spans a broad spectrum of vitamin D strategies. Immune systems, shaped by ancestors who endured malaria, dengue, and Old World pathogens, often display wide-ranging genetic defenses. But advantages intertwine with vulnerabilities. Admixed populations can inherit overlapping risks, like sickle cell traits alongside thalassemias, or multiple thrifty genes that heighten diabetes susceptibility in modern food environments. Vitamin D deficiency also becomes common when darker-skinned Caribbean families migrate to colder regions. Still, Caribbean ancestry stands as proof of biological synergy, a living map of how diverse histories can merge into resilient, adaptable human forms. If you're enjoying this video, don't forget to like and subscribe to the channel. Leave a comment below if there are any interesting topics you would like to learn more about. Now back to the video. Patagonian ancestry. Patagonian ancestry, embodied by the Selknam, Yagan, Kawiskar, Tehuelche, reflects one of the most extreme cold adaptations ever recorded. At the storm-lashed tip of South America, where icy winds and sleet define daily life, these populations evolved bodies that function like natural furnaces. Early measurements revealed exceptionally high basal metabolic rates. Even at rest, their physiology burned fuel rapidly, generating heat in a way few other human groups could match. Genetic clues hint at enhanced brown adipose tissue activity and variants that activate non-shivering thermogenesis, allowing warmth without trembling. Their diets, rich in marine fats, blubber, and proteins, fed this internal fire, converting calories into constant thermal output. These traits produced extraordinary resilience. Yagan divers could plunge into near-freezing waters with minimal temperature drop. Selknam families slept with scant clothing in sub-zero conditions, maintaining warm cores through metabolic heat alone. Even their circulation patterns seemed tuned to prevent frostbite, keeping extremities functional in damp, penetrating cold. Yet such specialization reveals modern vulnerabilities. Extremely high caloric needs become problematic outside cold environments. Overheating can occur in warmer climates, and fast-burning metabolisms may contribute to weight fluctuations or hormone strain when disconnected from ancestral lifestyles. These challenges grow sharper as descendants live far from the frozen lands that shaped them. Still, Patagonian ancestry stands as a testament to cold-forged endurance, bodies engineered by wind, sea, and the lonely brilliance of the far south. Japanese ancestry. Japanese ancestry carries a quiet refinement shaped by islands where rice paddies meet a cold northern sea. At its core lies a digestive signature almost unmatched, the ability to draw deep nourishment from both starch and shoreline. Coastal living fostered a symbiosis between diet and biology. Gut microbes in Japanese populations famously acquired genes from marine bacteria, allowing seaweed's dense fibers to break open and yield minerals, iodine, and rare sugars that most human intestines simply let pass through. Alongside this, generations of steady rice cultivation shaped a metabolism that handles starch with smooth efficiency through balance, a system tuned to release energy slowly, dependably, day after day. These advantages emerge from lives built around kelp-rich broths, raw fish, fermented soy, and winter coastlines. Those who could extract every calorie from sea vegetables, incorporate omega-3 oils into cell membranes, and withstand cold maritime winds passed on quiet strengths that still anchor Japanese longevity today. The result is a physiology marked by low chronic inflammation, efficient nutrient cycling, and an immune profile subtly enriched by ancient Jomon, Ainu, and Ryukyuan lineages. The same refinements carry modern risks. High iodine handling becomes a liability when seaweed intake swings wildly, and a metabolism designed for whole grains can falter under processed sugars. Alcohol flushing, common in this ancestry, protects some, but heightens cancer risk in others. Yet taken together, these traits form a lineage deeply shaped by tides, seasons, and sustenance, a maritime blueprint for endurance and long life. Romani ancestry. Romani ancestry carries a genetic story forged through hardship, a legacy shaped by migration, persecution, scarcity, and survival across a 1,000-year journey from the Indian subcontinent through the Middle East and Europe. Repeated population bottlenecks acted as intense filters where harmful mutations were often lost when only the hardiest individuals survived. Because of this, alleles tied to DNA repair, detoxification, and immune strength became more common. The result is a subtle but powerful resilience encoded in their biology, a constellation of survivor genes that supported endurance through famine, disease outbreaks, and forced displacement. This legacy still echoes today. Some Romani communities show robust immune responses and lower progression rates for certain infections, alongside metabolic efficiency shaped by generations of feast and famine living. Historical accounts often noted their ability to recover quickly from illness, maintain high fertility despite adversity, and endure long physical labor or performance with notable stamina, all expressions of a physiology sculpted by chronic stress and adaptation. But resilience has its costs. When a community begins with only a few ancestors, certain rare genetic conditions can become unusually common in later generations. Thrifty metabolism also predisposes some individuals to diabetes or obesity with modern lifestyles. These challenges intensify when ancestral lifestyles shift toward modern sedentary conditions. Still, Romani ancestry stands as a testament to survival. Genetics tempered like steel by centuries of upheaval, endurance, and unwavering cultural continuity. Levantine ancestry. Levantine ancestry traces back to the first densely settled towns of the eastern Mediterranean, compact stone communities where agriculture, trade, and urban life began. In these early cities, bodies adapted not just to grain-heavy diets, but to the pressures of crowding itself. Extra copies of the AMY1 gene helped turn wheat and barley into reliable fuel, allowing agrarian families to thrive on bread-centered meals. Meanwhile, living shoulder to shoulder in market streets and caravan hubs demanded a different skill, the ability to face a constant influx of microbes without being undone by them. Over thousands of years, Levantine populations developed broad HLA diversity, finely tuned inflammatory controls, and immune responses resilient enough to withstand the churn of trade routes linking 3 continents. These adaptations shaped daily life. People with Levantine heritage often show efficient carbohydrate digestion, moderate lactose tolerance from early pastoralism, and pigmentation balanced for both sun exposure and vitamin D production. Subtle traits, like tempered baseline inflammation accustomed to recurring exposure, reflect the legacy of bustling ancient cities where disease was omnipresent but survival persisted. Yet these strengths carry modern risks. High amylase can elevate dental conditions like periodontitis. Autoimmune conditions appear where immune systems become over-alert, and thrifty agrarian genes can fuel metabolic issues in calorie-rich lifestyles. Yet the deeper story endures, an ancestry refined by markets, migrations, and millennia of communal living, carrying within it the instincts of the world's first urban survivors. Sahelian ancestry. Sahelian ancestry evolves in a world shaped by contrast, a vast belt where rainfall arrives in sudden dramatic bursts, followed by months of dry winds sweeping down from the Sahara. In this semi-arid corridor, from Senegal to Sudan, bodies adapted to a climate of rhythm. Tall, slender frames, seen among Fulani, Tutsi, and related groups, maximize heat loss through long limbs and narrow torsos. Their build also reflects a life of movement, a physique shaped for covering miles between pastures. Sahelian populations show remarkable tolerance to dehydration. Sweat glands cool efficiently, and kidneys reabsorb salts and water with precision. Sahelian bodies typically begin sweating earlier, helping shed heat during long-distance travel. Among pastoral clans, widespread lactase persistence offered a liquid food supply during seasonal droughts, a trait tied to a Eurasian-derived mutation that spread through ancient cattle herding networks. Yet these strengths carry delicate balances. Salt retention becomes a risk for hypertension in modern diets. Bodies built for heat can struggle in cold or air-conditioned settings, and urban sedentary life often clashes with metabolisms engineered for motion. Still, Sahelian ancestry embodies a resilience tuned to seasons, to distance, and to the pulse of a landscape that changes not by the hour, but by the year. Austronesian ancestry. Austronesian ancestry carries the imprint of open oceans, voyages that crossed thousands of miles, guided only by stars, swells, and instinct. From the islands in Southeast Asia to the far reaches of Polynesia, these communities became history's master navigators. Among them, the Bajau sea nomads reveal a striking biological clue. Selection on genes, like PDE10A, enlarge their spleens, creating deep reservoirs of oxygenated blood that power long, graceful dives beneath the surface. Across the wider Austronesian world, patterns of endurance, spatial awareness, and calming under pressure reflect generations shaped by maritime life. Functionally, this ancestry excels where sea meets sky. Breath-hold diving triggers strong bradycardia and vasoconstriction, while well-developed core musculature stabilizes the body against shifting currents. Many show natural ease with star navigation, wave reading, and long hours on open water without fatigue or seasickness. Moderate pigmentation protects against equatorial UV during daily exposure on canoes and reefs. Yet ocean-forged strengths have limits. Physiology tuned for warm seas can struggle in cold, high-altitude, or landlocked environments, and enlarged spleens may pose risks in modern hyperbaric diving. Diets once rich in fish oils can also become unbalanced when replaced with processed foods. Still, Austronesian ancestry remains a legacy of exploration, bodies and minds shaped by wind, tide, and the boldness to cross the horizon. Iberian ancestry. Iberian ancestry carries a quiet biological refinement, an ability to draw remarkable power from sunlight. Across Spain and Portugal, generations lived beneath a Mediterranean sky that offered steady but not tropical levels of UV. In this environment, natural selection shaped a population with efficient vitamin D metabolism. Alleles that heighten vitamin D synthesis in the skin, streamline its activation in the liver and kidneys, and stabilize calcium absorption. This created a hidden advantage that strengthened bones, reinforced immunity, and supported long-term resilience against deficiencies that once crippled other regions. Functionally, this ancestry reveals itself subtly. Medium-toned skin balances UV protection with vitamin D production. Archaeological remains show dense bones and low historic rates of rickets, while epidemiological studies note strong skeletal health across modern Iberian communities. Athletes from the region often display durable recovery and bone integrity, reflecting vitamin D's influence on muscle and mineral balance. Even mood and seasonal energy, shaped partly by this nutrient, gain stability under Iberia's winter skies. But every biological strength has its shadow. Lighter pigmentation raised vulnerability to intense tropical sun during colonial expansion, and certain vitamin D receptor variants may slightly elevate autoimmune risk. In today's indoor lifestyle, even efficient vitamin D pathways can falter if sunlight becomes scarce. Still, Iberian ancestry stands as a testament to balance, biology tuned to draw sustenance from light, strengthening the body across seasons and centuries. Lowland Kushitic ancestry. Lowland Kushitic ancestry, embodied by Somali, Afar, and related groups, represents humanity's most refined adaptations to some of the hottest and driest zones on Earth, where temperatures regularly exceed 113 degrees Fahrenheit for months. In these environments, Kushitic populations begin sweating at higher core temperatures, conserving precious water, and when sweat does appear, it evaporates efficiently from deeply pigmented skin. Their kidneys are among the most water-efficient in humans, fine-tuned for constant scarcity. Their physiques, long-limbed, narrow, and extremely lean, radiate heat effectively, and their core endurance comes from thermal control. Heart rates remain stable, recovery is swift, and movement persists even under unrelenting sun. Genetically, lowland Kushitic groups carry signatures of ancient back-and-forth migrations across the Red Sea, a blend that shaped adaptations for both desert life and salt regulation, including variants that keep blood pressure stable when dehydration would otherwise cause collapse. But desert-forged traits come with modern trade-offs. Salt retention heightens hypertension risk in modern diets, low body fat makes cold environments far more challenging, and muted thirst signals can be misleading outside ancestral routines. Still, Kushitic ancestry stands as a testament to unbroken endurance, bodies engineered for a world where the horizon itself seems to shimmer with fire. Anatolian ancestry. Anatolian ancestry carries the imprint of the world's earliest farming cultures, communities that transformed wild grains into the foundation of civilization. In these sun-washed landscapes of Greece, Turkey, and the surrounding coasts, People evolved metabolisms finely tuned for a grain-rich diet. Extra copies of the salivary amylase gene allowed starch to break down almost instantly, turning bread and barley into smooth, steady energy. Gene variants influencing insulin sensitivity further stabilized blood sugar, ensuring that early farmers could work long hours on cereal-based meals without metabolic strain. This carbohydrate specialization became a strength that fueled dense settlements, monumental architecture, and the daily endurance of ancient laborers. Functionally, this ancestry remains evident today. Many individuals digest bread effortlessly, experience milder glucose spikes, and convert carbohydrates into reliable stamina for fieldwork, athletics, or long-distance travel. Saliva tends to break starch rapidly, teeth weather grain-heavy diets, and muscle cells absorb glucose with efficient precision. But finely tuned systems reveal their weaknesses in modern abundance. These thrifty genes can encourage weight gain when carbohydrates are constant and plentiful, and lifelong exposure to wheat has left some groups more prone to celiac disease or dental issues. The mismatch becomes sharper when ancient farming biology meets processed, calorie-rich diets. Still, Aegean and Anatolian ancestry speaks to humanity's first mastery of agriculture, bodies shaped by fields of wheat, enduring labor, and the early promise of cultivated grain. Ancient ancestral South Indian ancestry. Ancient ancestral South Indian ancestry reaches back to the earliest hunter-gatherers of the subcontinent, peoples who survived for millennia in dense forests, monsoon heat, and unpredictable food cycles. Their physiology carries the marks of that world: lean, heat-adapted bodies built for long-distance movement, and immune defenses shaped by constant exposure to parasites, insects, and contaminated water. One of their strongest hidden advantages was resistance to malaria. Variants such as sickle cell trait, thalassemias, and G6PD genes arose independently in forest regions, disrupting the malaria parasite's life cycle and saving countless children in prehistory. But another, quieter advantage lay in detoxification. Living off wild tubers, herbs, and honey meant ingesting plant toxins daily. Over time, these communities evolved high activity in enzymes like NAT2 and cytochrome P450, allowing rapid neutralization of natural poisons and smoke compounds. This biochemical resilience complemented an energy-efficient metabolism tuned for feast and famine living. Quick fat storage in abundance, quick release during scarcity, and muscular stamina suited to nomadic foraging. Today, tribal descendants still display this endurance, the ability to trek in humid heat, recover quickly from dehydration, metabolize wild foods, and mount strong immune responses. Yet ancient strengths bring modern challenges. Malaria protective genes can cause serious blood disorders if both copies are inherited. Thrifty metabolism accelerates diabetes risk, and detoxification pathways may overreact in urban diets. Still, this ancestry stands as a testament to deep survival, an ancient toolkit of endurance, immunity, and adaptability woven into the foundation of South Asian genetic heritage. Andean ancestry. Andean ancestry develops in a world ruled by altitude. Villages perched above clouds, terraces carved into cliffs, and air so thin each breath becomes negotiation. These highland groups built stable lives in vertical landscapes, adapting to a place where oxygen is scarce and cold bites hard. Across generations, mountain communities such as the Kala and Atacameno evolved physiques tuned for thin air, broader rib cages, deeper chests, and lungs that pull more from every inhale. Their circulatory systems became specialists in scarcity. Higher hemoglobin levels and dense blood vessels deliver oxygen with quiet efficiency. Altitude shaped more than lungs. Intense UV radiation, freezing nights, and diets centered on starchy mountain crops and llama-like livestock pushed further adaptation. Some genetic variants help regulate starch metabolism, protect skin from high-elevation sunlight, and sustain energy in cold, oxygen-poor environments. But trade-offs persist. Very high hemoglobin can thicken blood, raising cardiovascular strain, and people adapted to cold, dry air often struggle with heat and humidity at lower elevations. Nonetheless, this ancestry reflects a rare form of resilience, the ability not just to survive the sky's edge, but to turn thin air, harsh light, and stone-steep ground into a lasting home. Micronesian ancestry. Micronesian ancestry formed on some of the smallest, most exposed islands on Earth, coral atolls, with almost no rivers, thin lenses of rainwater in the sand, and sun that reflects off white reef at every angle. In this setting, bodies adapted to survive on the bare minimum. Kidneys became experts at concentrating urine, sweat glands released just enough moisture to cool without wasting water, and many islanders could work or paddle for hours in equatorial heat without the rapid dehydration that fells most visitors. Feast and famine cycles also shaped Micronesian metabolism. During breadfruit or fish abundance, storing fat efficiently was life-saving. During storms or droughts, being able to run on those reserves kept families alive. Tiny island populations also experienced genetic drift, a kind of random reshuffling where rare gene variants can become common after disasters. On Pingalap, a typhoon left only a few dozen survivors. One carried a mutation causing achromatopsia. Today, many descendants see only in shades of gray, disabling in bright daylight, but oddly useful for night fishing. These same strengths now create disadvantages. Salt-conserving bodies develop high blood pressure on modern, salty diets. Achromatopsia brings severe light sensitivity and low vision for many Pingalapese, with only a modest advantage in dim light. Micronesian ancestry reflects a biology shaped by sun, salt, and isolation, an island-forged resilience with no modern equivalent anywhere else on Earth. Celtic ancestry. Celtic ancestry is rooted in the cultures that once stretched across much of Europe, from the Atlantic coasts of Ireland, Scotland, and Wales to ancient communities in France and Central Europe. These regions share a landscape of short summers, long winters, and pale northern light drifting over cool, wind-carved coasts. In these conditions, high rates of lactase persistence offered steady calories when growing seasons were brief. Variants of the MC1R gene, particularly widespread in Ireland and Scotland, lighten skin to boost vitamin D production under dim sunlight. These same traits produce the unique red hair deeply associated with Celtic folklore. Alongside it, a unique HFE gene variant increases iron uptake, hypothesized to protect against anemia during famines or winters with limited protein. Together, these traits created constitutions well suited to the North Atlantic's dim, nutrient-lean landscape. These advantages come with modern precautions. Fair skin burns easily under strong sun, and the Celtic iron gene can cause iron overload if there are two mutated copies. Regardless, Celtic ancestry reflects a long adaptation to scarcity, transforming faint light and modest diets into enduring strength. Turkic ancestry. Turkic ancestry originates across the wide expanse of Central Asia, prominently in Kazakhstan, Kyrgyzstan, and Uzbekistan, with deeper roots in the Altai and Siberian highlands where early Turkic peoples first formed. These regions of freezing winters, open grasslands, and high-altitude migration shaped a genetic profile centered on endurance. This ancestry reflects a body adapted to environmental extremes, efficient heat conservation in sub-zero temperatures, steady oxygen use at elevated altitudes, and immune systems refined through close contact with herds and recurrent steppe epidemics. These traits form the biological backbone of nomadic life. One of the most distinct advantages appears in oxygen regulation genes. Some Kyrgyz and Altai populations carry variants in EPAS1, a gene also prominent in Tibetan highlanders, allowing stable oxygen use without producing excessive red blood cells. This protects the heart, prevents blood thickening at altitude, and supports long periods of exertion in thin air. In practical terms, it means sustained endurance during high mountain travel, fewer symptoms of altitude stress, and a calmer physiological response where oxygen is scarce. Yet these advantages come with modern challenges. Cold-adapted metabolisms may increase the risk of obesity and hypertension in sedentary urban settings, and historically strengthened immune responses can raise susceptibility to certain autoimmune conditions. Still, this ancestry leaves a quiet imprint, evidence of people shaped by altitude, winter, and the wide horizons that demanded both strength and adaptability. Yoruba and Igbo ancestry. Yoruba and Igbo ancestry emerges in the warm, open landscapes of southern Nigeria, where dense forests meet savanna. Over thousands of years, these environments molded populations with traits built for power, resilience, and heat tolerance. Deep melanin pigmentation protects against intense equatorial sunlight, preserving folate and guarding skin from UV damage. Long limbs and efficient cooling systems emerged under a hot climate, supporting both endurance in warm conditions and steady physical output. At the microscopic level, red blood cell variants, such as the sickle cell trait or hemoglobin C, offered protection against malaria, granting carriers far better survival odds in childhood. Many Yoruba or Igbo individuals carry the active form of alpha-actinin 3, a gene linked to fast twitch fibers that fire with exceptional speed. Paired with naturally high bone density, the result is a body built for explosive force, accelerating quickly, jumping powerfully, and withstanding impact with remarkable durability. Muscles contract with clean precision, and bones hold firm beneath it. These advantages carry certain costs. The same sickle cell trait that protects against malaria can produce severe blood disease when both copies are inherited. And dense, power-oriented musculature may be less suited for elite long-distance performance. Even so, this ancestry reflects a lineage shaped by the need to outlive both predators and parasites, an enduring testament to strength honed under pressure. Gran Chaco and Pampas ancestry. Gran Chaco and Pampas ancestry traces back to the hot, semi-arid lowlands of northern Argentina, Paraguay, and southern Bolivia, regions where summers reach extremes and food arrives in irregular rhythms. For thousands of years, indigenous groups such as the Com, Huichi, and Pilaga developed physiologies shaped by heat, scarcity, and constant movement across open plains. Many individuals descend from ancestors who navigated long distances on foot, giving these populations a natural ease with sustained activity. High sweat gland density, inherited from ancient lineages, supports efficient cooling in punishing climates. Their lean, long-limbed builds also disperse heat effectively, a body architecture suited to subtropical grasslands rather than cold forests. These populations often show exceptional tolerance to dehydration, maintaining circulation and stable core temperature even when water is limited. At the same time, their metabolism shifts smoothly between burning carbohydrates and fats, a trait forged through feast and famine cycles. This flexibility protects muscle during fasts, preserves energy when food is scarce, and prevents metabolic collapse under extreme exertion. Modern changes introduce their own risks. Metabolism tuned for scarcity can struggle with constant caloric abundance, contributing to rising rates of diabetes when traditional lifestyles fade. Through it all, this ancestry reflects a lineage built for persistence, bodies shaped to withstand hot winds, long walks, and the unpredictable generosity of the land. Caucasus ancestry. Caucasus ancestry centers on the mountainous regions of Georgia, Armenia, and Azerbaijan, where steep valleys and centuries of migration created one of Eurasia's most genetically diverse populations. This diversity is especially concentrated in traits linked to disease resistance. High overall genetic variation reduces the chance of harmful recessive gene pairings, contributing to lower rates of certain inherited disorders. Mountain life selected for strong cardiovascular capacity and antioxidant genes, while generations living at cultural and geographic crossroads through the Silk Road corridor fostered adaptability to new foods, climates, and pathogens. These strengths could all contribute to the exceptional longevity found in pockets of Caucasus communities. Caucasus populations also show unusually high HLA heterozygosity, meaning individuals often hold two different versions of key immune genes. This broadens the range of pathogens their immune cells can recognize. It acts as a genetic safeguard, enhancing defense against unfamiliar infections and supporting faster community recovery after epidemics. Yet immunity, this powerful, carries trade-offs: heightened inflammatory responses, and slightly elevated risks of autoimmune conditions. Caucasus populations reflect a long history of survival in a crossroads region where diversity became its greatest biological shield. Manchurian ancestry. Manchurian ancestry is formed in the broad, icy plains of Northeast Asia, regions where long winters, early agriculture, and shifting empires shape bodies to thrive on both hardship and harvest. Descendants appear today across northeastern China and parts of Siberia, carrying physiological traces of a landscape defined by cold air and carbohydrate-rich foods. Northern East Asian populations often maintain stable energy on grain-based diets. Their facial morphology, broad cheekbones, insulated sinus cavities, subtly warms the air they breathe, and their builds tend toward compact strength that suits life in sub-zero seasons. Manchurian groups typically carry elevated copies of the AMY1 gene, filling saliva with amylase that rapidly breaks down millet, wheat, and rice into ready fuel. This fast access to glucose pairs with traits that conserve heat: shorter limbs, sturdy torsos, and circulation adapted to maintain warmth during long months outdoors. Together, these features create bodies that turn grains into steady power while staying comfortable in deep cold. But there are modern caveats. Efficient starch digestion can encourage blood sugar spikes with constant refined carbs, and compact builds may gain weight quickly in sedentary life. Still, Manchurian ancestry remains a testament to survival shaped by frost and field, drawing energy from humble grains and endurance from winter itself. African pygmy ancestry. African pygmy ancestry traces back to the deep forests of the Congo Basin, where dense canopy, constant humidity, and a chemically complex ecosystem shaped one of the most specialized human adaptations on Earth. For tens of thousands of years, groups such as the Aka, Baka, and Mbuti lived in an environment rich in wildlife, but nutritionally unpredictable, demanding bodies that could endure exertion, heat, and frequent infections. Their small body size reduced calorie needs and allowed agile movement through thick undergrowth. High baseline immunity helped withstand parasites and chronic wounds that would debilitate outsiders, enabling long foraging treks in harsh conditions. These populations show elevated frequencies of fast-acting detox genes, such as NAT2 and variants in the cytochrome P450 family, allowing them to neutralize plant defenses found in bitter tubers, nuts, seeds, and certain mushrooms. This adaptation transformed challenging rainforest foods into safe, usable energy, providing a dietary safety net when game was scarce or famine threatened. Modern transitions reveal their trade-offs. Bodies optimized for sparse, wild diets may struggle with processed foods or high salt intake, increasing metabolic strain in new environments. Across the rainforest, their ancestry stands as evidence that human endurance can be biochemical as much as physical. Pashtun ancestry. Pashtun ancestry developed in the harsh uplands of Afghanistan and Pakistan, where steep valleys, thin soils, and long treks shaped bodies built for resilience. Life between the Hindu Kush and the arid plains demanded people who could move, adapt, and sustain themselves on whatever their herds and harvests offered. Many Pashtun communities show natural stamina on rugged terrain, reflecting a heritage of herding across mountains and passes. Their physiques often balance strength with leanness, aided by climates that reward efficient heat dissipation in summer and reliable warmth retention in winter. Pashtun populations carry high rates of lactase persistence, enabling lifelong digestion of milk. At the same time, early reliance on wheat and other cereals favored individuals who could convert starch into stable energy without rapid fatigue. Together, these adaptations created a system capable of turning yogurt, bread, and dry rations into sustained power for demanding landscapes. These advantages bring modern caveats. Efficient energy storage can lead to weight gain with sedentary living, and dairy-heavy diets may elevate cardiovascular strain in urban contexts. And yet, Pashtun ancestry reflects a physiology tuned to mountains and movement, strength drawn from simple foods, and the endurance to cross steep horizons. Arabian Peninsula ancestry. Arabian Peninsula ancestry emerges from deserts where heat is constant, shade is rare, and water is a precious, unpredictable visitor. Across these landscapes, Bedouin, Yemeni, Omani, and Gulf Arab communities developed physiology built for conservation. Kidneys that reclaim nearly every drop of fluid, sweat glands that reabsorb salt before it's lost, and circulatory systems that stay stable even during long hours of dehydration. This ancestry excels at fluid balance. Urine remains highly concentrated, even after salty meals. Sweat flows, but blood sodium barely shifts. Thirst signals remain muted until dehydration is severe, enabling controlled intake when water sources are distant. Combined with medium brown skin that shields midday sun and traditional clothing that amplifies cooling, these traits create a biology uniquely suited for arid endurance. But adaptations shaped for scarcity become fragile in modern abundance. Salt retention now fuels widespread hypertension, and muted thirst can mask dangerous dehydration, and bodies optimized for dry heat often struggle in humid or sedentary environments. These vulnerabilities grow sharper when climate and lifestyle no longer mirror ancestral deserts. Still, Arabian ancestry reflects a remarkable equilibrium, human physiology sculpted by sand, sun, and the discipline of survival. Mongmian ancestry. Mongmian ancestry emerged in the steep highlands of southern China and northern Indochina, where villages cling to ridgelines and daily life unfolds across thousands of vertical feet. Generations spent farming terraced slopes, carrying loads between valleys, and navigating thin, cold air shaped a population accustomed to long ascents and constant movement. Mountain living rewarded balance, stamina, and adaptability. People of ancestry often show strong leg power, reliable oxygen use at mid-altitude, and exceptional sure-footed endurance. Their mixed agricultural forager diets encouraged metabolic versatility, allowing them to shift between lean vegetable staples and dense rice-based energy sources. This ecological and cultural synergy supported a lifestyle where effort was continuous and terrain defined every task. Many Hmong-Mien individuals retain the fully active ancestral ALDH2 enzyme alongside a highly efficient ADH1B variant, breaking down alcohol rapidly and clearing toxic intermediates almost completely. Unlike neighboring East Asian populations that evolved the Asian flush mutation, these highland groups diverged early, never adopting the deterrent pathway. The result is a metabolism that handles fermented brews with uncommon ease, converting them cleanly to usable energy. This advantage, however, lacks built-in safeguards. Without the flushing response, overuse can become a modern risk. Across mountain ridges, this ancestry reflects a physiology tuned to altitude, effort, and the clarity of an older metabolic design. Finno-Ugric ancestry. Finno-Ugric ancestry took shape across the boreal north of Europe among Finns, Sami, and Karelians, who endured frozen lakes, dim winters, and months of near silence under snow. Survival here required more than tolerance. It demanded stability in an environment that rarely relented. Seasonal biology became finely tuned. Bodies adjusted smoothly to extreme swings in daylight, maintaining sleep, mood, and energy through long polar nights and endless summer days. Cultural practices like sauna bathing and cold plunges reinforced this physiology, training circulation to adapt quickly rather than go into shock. Compact builds and efficient fat distribution further supported thermal balance without excess strain. The most distinctive hidden advantage lies in silent heat production. Finno-Ugric populations show strong activation of brown adipose tissue, driven by variants in thermogenic genes such as UCP1. Instead of relying on violent shivering, their bodies convert calories directly into steady internal warmth. Core temperature remains remarkably stable even at rest or during sleep in sub-zero conditions, conserving energy while protecting vital organs. Heat rises quietly, evenly, and without fatigue. But this adaptation has modern flaws. Metabolisms built to burn fuel for warmth can clash with sedentary lifestyles, raising cardiovascular risk if activity declines. Even so, this ancestry reflects a rare evolutionary refinement: bodies that meet the cold, not with resistance, but with calm, continuous warmth. Mixed ancestry. Mixed ancestry takes shape wherever human communities meet, today in countries like Brazil, the United States, and South Africa, and historically in trading hubs from the Caribbean to Central Asia. These crossings create genomes that blend different evolutionary histories, each carrying adaptations shaped by distant environments. Some mixed ancestry individuals inherit intermediate skin tones that protect against UV damage, yet still allow vitamin D production, along with bodies and immune profiles shaped by more than one climate and disease environment. Notably, people with more diverse ancestry carry reduced recessive disease burden. When parents come from distant gene pools, their children are less likely to receive two identical copies of a harmful mutation. Studies show that outbred individuals have fewer of these risky pairings, lowering the odds of disorders like cystic fibrosis or certain blood diseases that only appear when both gene copies are affected. In this way, variety acts as a buffer against rare inherited conditions. But this protection has limits. Mixed ancestry does not prevent lifestyle-driven illness. Genetic diversity isn't a cure-all, but it consistently reshapes risk in ways that favor resilience. Hope you enjoyed this series learning about different genetic ancestries. Don't forget to like and subscribe, and if you want to learn more, check out these other videos.